This is going to be a continuation of the last lecture on Taylor's theorem. So I called it as Taylor's theorem 2. If you remember in the last lecture, I motivated, okay, why we should consider Taylor expansion, Taylor polynomial, what is its significance, and we also arrived at the so-called Lagrange's form of the remainder. Okay. And in today's lecture, I am going to do a slightly more general form of the remainder, from which we can deduce both Lagrange's form as well as Cauchy's form of the remainder. And because Cauchy's form is a little more subtle and also more useful, okay, it gives more control over the estimates of the error term. We will see that in action, perhaps if not in this lecture, in the next lecture. Okay, but today we will start with Taylor's theorem. Okay, statement, etc. So I'm not going to motivate the Taylor's theorem, etc. I'm going to simply state it now and write down the general form of the remainder and give a proof. You will see the proof is very, very parallel to the earlier proof with a slight twist. Okay, that we will see in a minute. So let us share the screen. Right. Okay. So what do we have? We have, as usual, J is an interval in R and F from J to R. Let us assume it is n plus 1 times differentiable. Okay, on J. So fix A in J, let X be also in J. Okay, so what does the theorem say? It says the following, and also let us do something more. Let us fix a natural number P, which is less than or equal to, let us say n plus 1. I don't believe I need any restriction on P, but let me just, to be on safer side, let me assume there is a restriction on P. Okay, this is a natural number. All right, okay. Then what do I want to do? I want to write fx approximately in terms of powers of x minus a, and then some remainder term. That's what we want to say. Then for all x in J, okay, we have fx, there exists, let us say C equal to C of x in J, so that f of a plus, let me write this general thing, a to the power k at a by k factorial into x minus a to the power k equal to 1 to n minus, okay, let me see what I want. I want to say it is f n plus 1 c by n plus 1 factorial into x minus a to the power p and x minus a to the power n minus p plus 1. Sorry, x minus c. So the last term is minus fn plus 1, the derivative at c by n plus 1 factorial. This is to be expected. Now this is x minus, see, in the earlier Lagrange's form we had x minus a to the power n plus 1. Here what I want is it is only up to p, and the rest of the things are given here, n plus 1 minus p, x minus c. I write the same thing, c equal to cx. Okay, earlier case. So how do I get when p equal to n plus 1? You see that I get what is called the Lagrange's form of the remainder. So call this system as Rn. Okay, so Rn is going to be fn plus 1 c by n plus 1 factorial into x minus a to the power n plus 1. When P equal to 1, that is called Cauchy's form. So that it here on the remainder is n plus 1 factorial into x minus a into x minus c to the power n. See, the powers are denoted. This x power x minus a to the power 1, x minus c to the power n. Okay, that's it. Okay. You may wonder why we need such different expressions for the remainders. See, remember, we want to approximate fx by means of Taylor polynomial. So the error is controlled by the remainder term. So then you have to estimate the error, namely the remainder. So sometime different forms give rise to better estimates. For example, in the case of binomial series, we are going to say Cauchy's form will give a better estimate. So that, as I said, will maybe in the next lecture, but let's not worry about. Okay, let's start with the proof. Proof, as I said, is exactly similar to the earlier case. So do you remember how we did? We defined f of t equal to whatever we wanted, okay, replace a by t. Do you remember that? F of t summation f to the kth derivative of f at t by k factorial into x minus t to the power k minus c into something. That's what we want to do. Okay, let me look at fx minus summation, okay, 0 to n f to the power k at t by k factorial and x minus t to the power n minus c into, in the case of earlier case, I had x minus t to the power n plus 1 here. Whereas here what we are going to do is, since we want, okay, this x minus a to the power n to be split as x minus a to the power p and x minus c to the power n plus 1 minus p. So we have to be slightly delicate. So what we do is very simple. I put it as x minus t by x minus a to the power p. Remember, we are assuming as usual x is not equal to a. Yeah. So we are considering these. First of all, you can see f is obviously differentiable, n plus 1 times differentiable. There is no problem. Right? Okay. Next, what is f of x? F of x equal to fx. Do you see that why? Because when I put x equal to t equal to x, this is 0. Right? And that's equal to, and whereas when I put x equal to t, this is going to be at kth derivative, that is same as fx. Therefore, it is going to be 0. Are you following? This is fx, and here what will be the first term? It will be f of t plus higher powers. F dash of t, x minus t, okay, and so on, right? These things will go 0 if I put t equal to x. So the surviving term will be fx, but there is a fx here, therefore it is 0. Yeah? Okay. Now what do I want? So I want, as I earlier, I want to apply Rhodes theorem. So to apply Rhodes theorem, what do I want? I have the a and x may be somewhere, it may be like this, or it may be like this. I don't care. So at one end point, the capital F vanishes. So at the other end point also, I want it to vanish. Therefore, choose C so that f of a is also 0. So what does that mean? That means what is C? Okay, that means f of a minus summation the kth derivative of at a by k factorial into x minus a to the power n, this 0 to n minus c, that is equal to c into, that's it. Because when I put, what do I want to put? I want to put t equal to a, therefore x minus a by x minus a, therefore c. Therefore the c must be equal to this. You understand this? Therefore c is this. It is immaterial for us, but I am just writing, okay? Very good. So there is a c, so that this happens, f of a is 0, right? Therefore by Rhodes theorem, okay, by Rhodes theorem, so there is a c between a and x. This c depends on x, okay? So that f dash c is 0, right? So we want to compute f dash t and put f dash c equal to 0. That will give us what is this capital C. See, this capital C should not be confused with the small c. Okay, I'm sorry for the notation, but I think the idea is clear. Okay, right. So what is f dash t? Let us look at a typical term. Okay, see, now remember this is capital F of t, right? The fx, therefore this is a constant. So when I take derivative, this will be 0. So what are the typical terms? Typical terms of this. One of the summands in this finite sum 0 to n and the last term. So we want to look at what happens. Okay, what is the first term? First term is again constant term. Yeah, f of okay, k equal to 0, that is same as 1. K equal to 1, that will be, are you following? Okay. Okay, so what is the kth term now? Kth term is going to be kth derivative of t by k factorial into x minus t to the power k. So I want to apply d by dt of this. So what is this equal to? That's going to be k plus 1th derivative of t by k factorial into x minus t to the power k minus, why do I know minus? Because I'm going to differentiate this and t has a minus sign, so I'm putting minus. Okay, so this is going to be fk of t, okay, by k factorial into k into x minus t to the power k minus 1. I'm differentiating this. Yeah, and what will be d to the t of the next one? F of k plus 1 of t by k plus 1 factorial into x minus t to the power k plus 1. That is going to be f of k plus 2 of t by k plus 1 factorial into x minus t to the power k plus 1 minus f of k plus 1, the derivative of f at t by k plus 1 factorial into derivative of this. The derivative of this is going to be k plus 1 into x minus t. There is a minus sign that I brought out, therefore x minus t to the power k. Now notice that k plus 1 factorial is k plus 1 into k factorial. K plus 1 cancel. So what am I getting? K plus 1 to derivative f at t in times x minus t to the power k, denominator k factorial. You can see this cancels. Yeah. So this is the telescopic sum cancellation. Okay, cancellation. Okay, telescopic sums and cancellation takes place. Right? Because f of t, okay, derivative of this will be f dash of t. Next one will be it's into x minus t. Okay, so minus f of t, that's it. Okay, and d by dt of f dash of t into x minus t. I'm sorry, I'm going fast, I'm making mistakes. So let us look at d by dt of f of t. Okay, this is going to be f dash of t. And d by dt of what is the second term? F dash of t into x minus t. Okay, that is going to be f double dash of t into x minus t minus f dash of t, okay, okay, plus f dash of t into derivative of d by, that's a minus, therefore it's just f dash of t. And what will be d by dt of second? See, if you had attended the last one, you know what I'm doing. This is exactly what we did in the last lecture. This is going to be f third derivative of this by 2 factorial into x minus t whole squared minus f second derivative of t. There is a 2 here into x minus t. The minus sign is brought on here. Therefore, 2 factorial. The 2 cancels. You can see this is what we did. Okay. So what is left out will be, okay. So the only when I look at the what is the last term? The last term is d by dt in the sum. That is fn of t into x minus t to the power n by n factorial. So that is going to be fn plus 1 of t x minus t to the power n by n factorial minus, okay, fn of t, and there is a minus sign, okay, n, not minus, just n, into x minus t to the power n minus 1 by n into n minus 1 factorial. As we saw, this term would have cancelled with the earlier term. This would have cancelled with some other term here, right? So surviving term is this. And now what is the last term? Last term is going to be minus c d by dt of x minus t to the power p by x minus a to the power p. Okay, what is the derivative? Remember, x and a are constant. This will come out. Minus c will remain. And I have to differentiate x minus t to the power p. Therefore, p will come out. And x to the power minus t into p power minus 1. And there is a minus sign. Therefore, the whole thing gives me c in times x minus t to the power p minus 1 c times p times x minus a to the power p. You understood that? Therefore, f dash c equal to 0 if and only if this is, okay, remember there is a minus sign, okay, all these things are with a minus sign. Go back, there is a minus sign here, okay, my f of x is all these things with a minus sign, therefore there is a minus sign, okay. That means minus of this, that is f n plus 1 t x minus t to the power n. Now it's a c, therefore it's a c by n factorial, okay, plus c times p times x minus t to the power p minus 1 by x minus a to the power p is 0. Yeah, therefore c times p times x minus, again I put c here, x minus c to the power p minus 1 x minus a to the power p equal to fn plus 1 of t x minus c to the power n by n factorial. Therefore, c equal to, okay, 1 by n factorial into p f to the power n plus 1. Again, c here. Yeah. C, okay. Then what do I have? I have x to the power x minus a to the power p, that goes above. Then x minus c to the power n. This is, I would divide, this is p minus 1, therefore it's n plus 1 minus p. So my c is this. Okay, pause, review, proceed. Right? Okay. Now let's go back. What do I know? I know that f of a is 0. Okay, I chose C, so that f of a is 0. But what is f of t? F of t was fx. Therefore, let me say f of a, that is equal to 0, equal to c minus, okay, f to the power k at a by k factorial x minus a to the power k equal to 0 to n minus c, but minus c is this object. Let me just keep this c as here, right? Yeah. So x minus a to the power p x minus t, sorry, x minus a to the power b by x minus a to the power p. Remember, it is x minus t to the power p. What is my f of a? c x minus t to the power p, but when t equal to a, this x minus a by x minus a. Therefore, it's 1. That is just a c. Do you follow that? Yeah. So this is just a c. But I know what is c. Therefore, fx minus fk at a by k factorial into x minus a to the power k equal to 0 to n minus f to the power n plus 1 at c by n factorial into p and x minus a to the power p and x minus c to the power n plus 1 minus p. This is equal to 0. That is fx equal to this. So this is what we wanted to prove. Okay. Please, do you follow that? The proof is exactly similar if you have done earlier case. So I hope you have done that. Okay. Right. Okay. Now I want to make some remarks about Taylor's theorem. There are few things which students should learn. Now this we will denote by Rn of x to be this one fn plus 1 c by n factorial into p into x minus a to the power p into x minus e to the power n plus 1 minus p. Right? Okay. And there is no standard notation for Rn. It may be Rn plus 1 because n plus 1 the derivative comes. I am calling it Rn because I have taken nth degree Taylor polynomial, whatever the remainder, it's a nth remainder. That's what I'm calling. But I don't think there is a universal agreement about that. Okay, your teacher or textbook may vary. Okay, just be aware of that. That doesn't matter. Anyway, is that all right? Okay. Now what do I want? The first thing you should notice is we chose a C, right? See, we chose a C between A and X such that f dash C is 0. Notice that the C is never unique. There may be many C's because how did we use? We use Rhodes theorem. So Rhodes theorem would have done like this. So these are the points. At the end point is the same value. This could be C, this could be your 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 C. So there are many possible C's. Therefore, it's not unique. You understand that? But this is a very crucial. But on the other hand, this is a, and also C depends on X. A is fixed, therefore I do not worry about. Okay, on X. Okay, this C is not unique, but this expression is unique. This R and X, this is well defined. Why it's well defined? Because fx minus this Taylor polynomial equal to R and X. So whatever C it shows, okay, you understand that fn plus 1 to derivative C, but there is a C here also. It will keep varying. Suppose C1 and C2 are there, fn plus 1 at C1 by n factorial p x minus a to the power p x minus C1 to the power n plus 1 minus p will be equal to n plus 1 to derivative of f at C2 n factorial by p x minus a to the power p x minus C2 to the power n plus 1 minus p. You understand that? Therefore, this is well defined. Therefore, it's a function of x. Okay, therefore remainder is a function of x. That's the first thing. Okay, even though this is not, C is not fixed. Do you follow that? If you want, please rewind, because these are the things which are never explained often. Okay, you just arrive at this definition, theorem proof, you think that you had understood. Okay. Next point is the following. R and X, see, it looks, see, just because you think this is, see, as X varies, okay, this is not, this looks like a polynomial, but it's not a polynomial. Why it's not a polynomial? Because this object and this object, see, these are not constant. As X varies, C also varies. You understand? Therefore, it's not a polynomial. And how do I conclusively prove R and X need not be a polynomial in general? Because if Rn is a polynomial, that's going to be f of x minus Tn of x, where Tn of x is what I call the Taylor polynomial. Okay, maybe if you also call it T n fx or T n fx or whatever it is, Taylor polynomial of degree n of f at the point x, and also you have to say at a. Anyway, okay, suppose this is a therefore that would mean if this is a polynomial, we know this is a polynomial, therefore it will turn out fx is a polynomial, but f could be any arbitrary differentiable function, right? N plus 1 time differentiable function. Do you understand? Therefore, this, okay, Rnx is a well-defined function, but it need not be a polynomial. Okay. Next, remember in the first lecture also I said the idea is, therefore I want to say fx is approximately equal to Tn of x, where Tn of x is the nth degree Taylor polynomial. Okay. Therefore, fx is going to be Tn of x plus Rn of x, equality for all x in J. Right. Therefore, when I'm approximating, what is the error I'm doing? Tn Rn of x. So I want an estimate for Rn of x. You see, that's where the two forms of the remainder will help us. Okay. Depending upon the situation, either this may work, Lagrange's form may work, or it may not work. Then I have to choose Cauchy's form. Okay. We will see that. The best thing is, do not worry about remembering any of these things. Okay. If you want to understand mathematics, especially analysis, just try to understand the subtle points, go through the proof, try to ask why it works, why it does not work, and that's good enough. You will slowly see you become a master. You yourself can create mathematics. Okay, good. Right. Okay, so I have to estimate Rn of x. The next thing is, suppose my f is infinitely differentiable. Okay, that means fk of x exists for all k in z plus, that is, and or for all x in j. It's infinitely differential on j. Then instead of polynomial, I can actually form the following series: 0 to infinity fk of at a by k factorial into x minus a to the power k. Do you understand this? Yeah, this is called the Taylor series of f at a, because it is in the powers of a. Because all these things make sense now, right? So what would you guess? You would think the function fx must be equal to this Taylor series. This is what very natural guess would be. Do you follow that? But in general, it need not be true. What can go wrong is, first of all, this series may not converge for every x in J. Is that clear? So may not converge for all x in J. And next, even assuming it converges at x in J, okay, the sum of the Taylor series may not be fx. Okay, do you understand this? Okay, so these are the problems with Taylor series. Even the Taylor polynomials are a good approximation, the Taylor series by itself, notice that this series makes sense for every x. Makes sense meaning I can form the series. Whether it converges for each x in A, I do not know. It may or may not converge. Number one. Next, suppose it converges at some x in J, then the sum of the series, is it equal to fx? I do not know. It may or may not happen. Okay. So if it happens, then you say the function f is represented by the Taylor series around A. If it happens in some interval around A, then you say that. You will see that. Okay. Let us look at some example first. Now, the first thing is, when I want to say fx equal to this. Okay, for which x? Fix x in J. I want to know whether this happens, right? Now, what is, we have to recall something about infinite series now. Suppose I have series of thing k equal to 0 to infinity 1. Okay, when do I say it converges? So form the partial sums a1 to ak. If these partial sums converge to some number s, then I say this converges. And I say the sum equal to this s. Do you understand that? There is no meaning to the sum. What you do is partial sums you take, okay, a1, a0 to ak, okay, and if s is converged to s, then I say this infinite series is convergent and it converges to s, and the sum is s, right? Therefore, when I want to say this sum equal to s, what does it mean? I have to take the partial sums. But what are the partial sums? Partial sums are k equal to 0 to n of this object. But what is that? That is tn of x. You understand that? That is, so this happens, okay. When does it happen? Only when tn of x converges to f of x. Okay, I am fixing x now. Therefore, it's a okay sum of numbers. Okay, series of real sum of real series. Okay, it's a series of real numbers. So this, okay, sequence of real numbers must converge to this real number. Right? Now let's look at what does that mean. That means fx minus tnx, okay, must converge to 0. But what is fx minus tnx? That's what Taylor series says. Taylor series says fx minus tnx is Rnx. Therefore, okay, fx equal to Taylor series if and only if Rnx converges to 0. Notice that all of these are point wise. I fix a point x and j. I am talking about this question. Do all of you understand? Pause, review, and proceed. Okay. Now let's look at a very simple example and look at how to prove that. And it will also illustrate some points which I talked about the function. So let f be a function, okay, f of x equal to log of 1 plus x. So log of 1 plus x must make sense, therefore 1 plus x must be positive. That means x must be greater than minus 1. Therefore this function is, the domain is minus 1 to infinity. Right, this is the function. Now is it infinitely differentiable? Yes, all of you know that. Okay, you human may know the Taylor series expansion of this in your calculus course. Anyway, this is 1 by 1 plus x. And f double dash of x is minus 1 by 1 plus x whole squared. F third derivative of x equal to, there is a minus, therefore 2 into 1 by 1 plus x whole cubed. And fourth derivative of x will be, this is 3 goes, therefore there is a minus sign, minus 3 into 2 into 1 by 1 plus x to the power 4. So by induction, it will follow fn of x will be, look at that fourth derivative, therefore it's going to be minus 1 to the power n minus 1, yeah, okay, into 1 by 1 plus x to the power n plus 1. Just let's make sure it's correct. When n equal to 1, it's f dash x. This is positive 1 by 1 plus x. When, sorry, n equal to 0. Yeah, all right. Let us do that. N equal to 1, f dash x equal to, I want 1 by x plus 1. So what did I get? F dash, f dash, f dash. Oh, so 3, there is no increasing of power, right? This fourth power, sorry, that's correct. So I'm sorry. You see that I made a mistake? Yeah, this is just n. Just to make sure I'm doing it correctly. Okay, when n equal to 1, this is minus 1 to the power 0, that is 1 by 1 by x. When n equal to 2, there should be a minus sign, 1 by n plus x squared when equal to 3. Yeah, therefore there is a n minus 1 factorial. Yeah, when n equal to 2, okay, n equal to 3, this is positive, 2 factorial, n equal to 4, it should be 3 factorial by 1 plus x cubed and minus n. Yeah, okay. So prove it by induction. So this follows by induction. So let me write it for, so that I don't get confused later. Minus 1 to the power n minus 1, n minus 1 factorial by 1 by x to the power n. Do you understand this? And this is true for all which x? This is true for all x greater than minus 1. Therefore, I can form the Taylor series. Okay, what is the Taylor series? At x equal to 0, of course, of f. That is going to be summation, okay, n equal to 0 to infinity of nth derivative of this at 0 by n factorial into x power n. Yeah, right. But what is this in this case? So that is equal to, I know what is f for n, right? That's 0. It is going to be, this is 1. Therefore, summation n equal to 0 to infinity minus 1 to the power n minus 1, n minus 1 factorial by n factorial into x power n. Do you understand this? Because when x equal to 0, this goes away. But that is going to be, so minus 1 to the power n minus 1 by n, because n minus 1 factorial will be n into n minus 1 factorial, they get cancelled into x power n, 0 to infinity. This is the Taylor series. Yeah, okay. Now you see that for each x greater than minus 1, I have formed the Taylor series, right? Now you want me ask when this sum is convergent, when this series is convergent. You can apply ratio test. When I apply ratio test in modulus, what do I get? 1 by n plus 1 and x to the power n, everything is modulus by n by, this is the same n, okay, okay, x to the power n plus 1 by n by mod x to the power n. This is give me n by n plus 1 into mod x. Therefore, it, okay, it goes to mod x. Therefore, mod x must be less than 1. You see that? Therefore, the Taylor series is convergent only if mod x is less than 1, even though I can form the Taylor series for all x greater than minus 1. Therefore, the Taylor series does not converge, okay, if x is, mod x is greater than 1. You see that? When mod x is greater than 1, the Taylor series is not going to converge, right? So this proves what I said. The Taylor series, what happens? May not even converge for all x and j. Okay. For this function, the j was minus 1 to infinity, but then the convergence is going to take place only in the interval minus 1 to plus 1. The open interval minus 1 to plus 1. Okay. Do you follow that? Okay. Right. Now let us see what happens at x equal to 1. Does it converge? Does the Taylor series? What is that? That is going to be minus 1 to the power n minus 1 by n. Yeah, all of you know from your 12th standard onwards, this is alternating series which is convergent. And convergent. That means the Taylor series for f at 1 converges. Have you understood? Now comes the next problem. Please pay attention. These are the subtle games which are you rarely explained in analysis because you only prove theorem after theorem. Don't spend what it really says. So the Taylor series, okay, of f converges at 1, but that's no guarantee that f at 1 equal to this. Okay, that's a question. This is not guaranteed. Do you understand? But what is f at 1? That is log 2. So if I prove, okay, this series, of course I know is convergent, but it converges to the value of the function at 1, I am through. Then it will, therefore the sum of the series is going to be log 2. Do you understand this? Pause, review, proceed. So the what we have done? We have done that this Taylor series at x equal to 1 is alternating series, therefore it's convergent. So the next question is, it may converge, but does it converge to the value of the function at 1? What is the value of the function at 1? That is log 2. So my question is, does this converge to log 2? But if it converges, it will be log 2. So the real question is, does it converge to f at 1? We had already seen, when does the Taylor series f at x converge to fx? If and only if the remainder r and x goes to 0, right? So let us work it out. So what is r and x? Okay, so this happens, that is if and only if r and x goes to 0, that is r and 1 when x equal to 1. Okay, right? Now let's go look at what is r and x. In general, r and x, we will use Lagrange's form of the remainder. Okay, is going to be fn plus 1 at c by n plus 1 factorial into x minus a to the power n plus 1, right? Therefore at 1, what does it mean? Therefore it is between 0 and 1. My x is going to be 1, and therefore and a is going to be 0, right? A is 0 and x equal to 1, right? And therefore my c is positive, right? Let us cut. Now what, therefore what is r n at 1? That is fn plus 1. But I already know what is fn plus 1. Where did we compute? I said we will do it somewhere. So fn plus 1 is going to be minus 1 to the power n. When I take absolute value, I can ignore, and that is I want n plus 1. Therefore, it is n minus 1 factorial will become n factorial by 1 plus c to the power n. Okay, let me write it. So fn plus 1 at x, we have seen it is minus 1 to the power n, and n factorial by 1 plus x to the power n plus 1. Am I right? Minus 1 n. Okay, n meaning n factorial. Okay, 1 plus x by n. Yeah, I am needing n plus 1, therefore it will be n factorial by x plus 1. Yeah, correct. Yeah, and therefore modulus fn plus 1, sorry, modulus of Rn at 1 is going to be fn plus 1 at c, that is modulus goes, therefore there is an n factorial, okay, right, and divided by c1 plus c to the power n plus 1. Remember, 1 plus c is greater than 1. Okay, let me write it anyway. N plus 1 factorial, and this a is 0, x is 1, therefore 1 to the power n plus 1. Okay, that's guys out. Are you following? I hope I'm not confusing you. 1 plus c to the power n plus 1. fn plus 1c I have written n factorial by this, and this is a is 0, x is 1, therefore it is 1 to the power n plus 1 if you want. Okay, therefore modulus I have to put. Okay, so what is this? This is going to be 1 by n plus 1 into 1 by 1 plus c to the power n plus 1. But 1 by c is greater than 1, therefore 1 by c to the power n plus 1 will be greater than 1, therefore 1 upon that will be less than 1, therefore this will be less than 1 by n plus 1, right? 1 by n plus 1, that goes to 0. Therefore, what do you think I have proved? I have proved that, okay, the Rn remainder term at x equal to 1 goes to 0. That means this series is convergent. It converges to f of 1. But f of 1 is log 2. Therefore, we have proved the sum of alternating series log 2. Usually, we prove only convergence. There are, to the best of my knowledge, there are two ways of finding the sum of alternating series, standard alternating series. One is using this log of 1 plus x Taylor expansion and proving that at x equal to 1, the Taylor series converges. And hence, we get the log 2. Other trick is using Abel's theorem. That may be in some other video in future. Okay. So you can see we just used Lagrange's theorem. Just try to understand, could you have proved this using Cauchy's theorem, Cauchy's form of the remainder? Remember, it will be x minus a, right, to the power n plus 1. That's x equal to 1. But then this will be c to the power n plus 1. You understand that? Okay. Just to make sure that you understand, I'm giving an exercise. Okay. Okay. See whether how to, can you prove this using Cauchy's form of remainder? Because I'll have, yeah, I know it's a little demanding because analysis is usually theorem proof, and all the subtleties are never brought out usually, because teachers, even though they understand, the students may find it difficult. But it's my belief all the time, yes, students may find it difficult, but you slowly explain to them so that their standard also raises. It's something like, if you're a baby and you don't know how to speak one word, one syllable word, etc., your mother only keeps talking one syllable word, you will never pick up the language. It's difficult, but your mother keeps talking so that you slowly learn. The same way, I believe even in mathematics, just because students find it difficult, I should not stop it. I will try to explain it once again and try to go through. Okay, I hope you understand my principle. Please go through it. Okay, if you're doing this kind of thing, you will appreciate how subtle analysis is. Analysis is analysis. You have to analyze the things much more carefully. Yeah, I think you will love it. Let's meet again. Bye. Take care. Stay safe.